Hello and welcome to Airborne Laser Scanning System or LIDAR systems. Today I'm going to go through the basic principles of LIDAR systems and also some of the main applications of LIDAR systems. So let's start. The term LIDAR stands for Light Detection and Ranging. And it's important in the beginning to mention that I'm focusing today on airborne LIDAR system, where the LIDAR scanner is mounted on an aircraft for scanning large areas. Because the LIDAR system could be mounted on a drone, as you can see here. So the LIDAR system would be somewhere here. And this is mostly used for scanning small areas locally to produce some kind of 3D data of the scanned area. And also, there are some terrestrial LIDAR scanning systems, as you can see here. And the same principle of LIDAR systems is exploited for self-driving cars, in fact. So they will mount the system somewhere above the car, and then the LIDAR system will start to collect data for all of the objects around the car. The main components of any airborne LIDAR system are three. The laser scanner, which is the most important one, and also the GPS system or GNSS system, Global Positioning System, and finally the inertial navigation system. In some systems, this INS, Inertial Navigation System, might be called IMU, Inertial Measurement Unit. So the first component, the laser scanner, will emit the laser pulses to the ground surface, and then the laser pulse will hit the ground surface and then it would be reflected back to be detected by the laser scanner again. Okay, so this kind of laser pulses would be reflected by the ground surface or any feature on the ground surface, like the trees or buildings, cars, any feature on the ground surface. And the GPS system is important for calculating the coordinates of the aircraft. We have here a GPS receiver. There would be a GPS receiver here. And then on the ground, there would be a GPS station. And this will help the system to calculate the coordinates of the scanned points or the scanned area. And the aim of the INS system is collecting information about the orientation of the scanner in the space. By putting all of the information now from the laser scanner, from the coordinates recorded by the GPS system and the orientation of the scanner in the space, putting all of these kind of information together to calculate the final coordinates. Now let's look inside the aircraft here, guys, to see some more details about the LIDAR scanning system. As you can see here, this is the body of the aircraft. We have a GPS receiver here. And this is the laser scanning system. Here we have a control unit for recording the data, guys, as you can see here. And this is the laser scanner here that emits and receives the laser pulses. And here we can see the IMU, Inertial Measurement Unit, or as I mentioned in some references, you will see INS, Inertial Navigation System. They are both the same for calculating the orientations of the laser scanner in the space. So now all the data gathered from the GPS, from the laser scanner, IMU, would be recorded here, and then it would be processed using a PC or laptop to generate the final results that we call raw LIDAR data. That includes the coordinates of the scanned points, X, Y, Z, and also sometimes more information about the scanning angle and the intensity of the scanned objects, etc. So all sensors or laser scanners perform the same way. They measure the distance between the scanner and the ground. Using this very simple relation, so the distance or the range between the scanner and the ground is the speed of light times the time required for each laser pulse to go to the ground and return back to the scanner. So again, all LiDAR systems have the same principle. In fact, the differences between the systems might be in the laser power or the spot size and the swath angle or the scanning pattern. I will go through these now in some detail, as you will see. So let me summarize this in a different way. Now here we have the aircraft here flying in this direction. The laser scanner is scanning the ground surface, as you can see here. So if you have buildings or something like that, like here, we can represent this like in laser spots, as you can see here. These spots on the ground, these are the same spots here. And each laser pulse or spot would be reflected back to the laser scanner. And we have the GPS system. We have some ground station system and also the GPS receiver on the aircraft to determine the coordinates of the aircraft or the laser scanner. Okay, and don't forget the inertial measurement unit here that will provide information about the orientation of the aircraft or the scanner, and then all of the information gathered from the GPS system, IMU system, and the laser scanner as well would be processed to produce the final raw LiDAR data, as I have just mentioned. That includes X, Y, Z, etc., some more information. So we can represent each laser pulse reflected by the ground as a spot, as you can see here. And the spot size, guys, depends on the flying height of the aircraft and also type of the laser scanner as well. And also one of the differences between LiDAR systems is the swath angle. The swath angle is this distance that could be covered across the flying direction. From here to here, this is the swath. And it depends on the field of view angle, this angle here of the scanner. And the scanning pattern could be different from one LiDAR system to another. For example, this is called oscillating scanning mechanism, where the laser scanner moves in this direction, as you can see here, to reflect the laser pulses to the ground. And the scanning pattern on the ground could be represented by this. And we have also rotating scanning mechanism like this one. So the mirror of the scanner will move like this, and the scanning pattern on the ground would be like parallel lines, like these lines, etc. So this is called rotating scanning mechanism. And also we have nutating or palmar scanning mechanism, this one here. So the scanning system like circles. So this is a rotating scanning mechanism. And this is oscillating scanning mechanism. And finally, we have the fiber scanning mechanism, as you can see here. But in the end, all of these different kinds of scanning mechanisms have the same principle, the same main principles, which is measuring the distance between the scanner on the aircraft and the ground surface or any object on the ground surface. Okay, the spot size, as I mentioned, might be different, the swath angle, the scanning mechanism, the laser power, all of these would be, there might be differences between all of these kind of sensors, but in the end we will have a range or a distance between the laser scanner and the ground. Okay, now the echo detection. Let's speak in more details about the echo detection system. Let's say that there is a laser pulse that's emitted by the sensor, and then it would be reflected by the ground or any object on the ground, in fact, and then it would be received back by the sensor's detector. The time difference between the emission and the reception corresponds at twice the distance to the object. Okay, so let's say that this is the laser scanner here, and this is the ground surface. So a laser pulse would be emitted and then it would be reflected back. Okay, each laser pulse will travel the same distance twice. So because of that, for calculating the range, if you remember the relation, it was the speed of light times the time required for each pulse divided by 2, because each pulse will go the same distance twice. And the detector will help us to calculate this time, and then the speed of light is known and constant. Based on this, we can calculate the range or the distance between the laser scanner and the ground surface. And the reflection of each laser pulse depends on the shape and size of each object. For example, if we have here in this case a slope echoes, like here let's say we have stairs or something like that, so each laser pulse would be reflected by multiple echoes, as we can see here. Multiple echoes. This is one laser pulse, but it would be reflected back by multiple echoes, and this is very important thing and helpful for the determination of the differences in elevations of the topography. And if we have a vegetated area like this one, so the laser pulse would be reflected following the pattern of the vegetation in the scanned area. Now, after collecting all the data from the GPS, from the inertia measurement unit, from the laser scanner, okay, we can finally generate the raw LIDAR data. So usually raw LIDAR data, guys, will have an ASCII format for the generated file that contains all the information about the scanned area. So these numbers here, as you can see here, this is raw LIDAR data. So these numbers, guys, represent, as I mentioned, so the coordinates of each scanned point on the ground surface or any object on the ground surface, and also additional information about the scanning angle, the intensity of the object, etc. So this file mostly will have an extension of ASC from ASCII, and also it might have an extension of LAS from laser, might have an extension of TXT, the symbol well-known one. So these are all kind of extensions for the raw LIDAR data before any post-processing. So now, guys, to visualize this kind of data, to convert all of these numbers into an image, we need to use a software to convert them into an image using the coordinates. For example, we have coordinates x, y, and z for each scanned point. The software can use the x, y for locating each point, and then the z value to generate a shaded image, for example, like this one here. So in this case, we have converted the raw LIDAR data into a shaded relief, as you can see here, and this is forested area. So here we have trees, and here we have clear cut area, no trees at all, as you can see these areas here. And this format is called a raster format because it is an image. One of the most important applications of LIDAR systems, guys, is generating the digital terrain models or digital surface models. In this example, as you can see here, we have this scanned area using a very high resolution LIDAR system. You can see here mountains, and here we have a lot of buildings. As you can see here, we have a lot of buildings in these areas. Okay, and here we have some kind of topography, different elevations. This is a color coded. The high areas will have white color, and then the low areas will have this kind of green and gray color, etc. And this is called digital surface model. Digital surface model represents the ground surface and all the features on the ground, all the buildings, cars, trees, everything on the ground surface that would be included in the digital surface model. Now, removing all the objects from the ground surface, like removing all of these buildings here, okay, all the trees, all the cars, any object on the ground surface would be called filtering raw LIDAR data. So after we filter the raw LIDAR data, we can generate a digital terrain model. That's called DTM. So now the main difference between the digital surface model and the digital terrain model is that, so the digital surface model represents the ground surface, the terrain surface, and all the features on the ground surface like trees, buildings, houses, cars, vegetation, etc. Now, after filtering this digital surface model and removing all of the objects, trees, buildings, cars from the digital surface model, we can generate digital terrain model. And this is just the terrain, the topography of the ground without any building or tree or any object that might be exist in this area. Now let's speak in more details about the filtering of raw LIDAR data, guys. Let's return to our example for this forested area here. This is a digital surface model of this forested area. We have here trees, okay, and here we have, as I have just mentioned, clear-cut areas with no trees at all. Here we have few trees, not very dense forest here. Here I can see a valley, yeah, and some roads through the forest, etc. So after filtering this digital surface model, we can generate a digital terrain model like this one here. If you look at this case here, this is the filtered data. We have just the topography, we have just the terrain, all the trees were filtered and removed from this area. Now I will try to simplify the principle of filtering raw LIDAR data. Let's say that these are the laser pulses here in blue. We have here the ground surface and we have here some buildings, trees, houses, etc. So the laser pulses were reflected by all the objects, the ground surface and all the objects that cover this surface. So now filtering this kind of raw LIDAR data means that we have to classify each point, each laser pulse here, as ground or non-ground point. So these points here, all of these points here, that have reflected by the buildings and trees, etc., are non-ground points. And these should be identified as non-ground points and removed from the raw LIDAR dataset, so that in the end we will have just these points that are reflected by the ground surface, and these represent the terrain surface. From these points, we can generate the digital terrain model. Okay, so these points in red here, again, these are non-ground points. This should be removed from the raw LiDAR dataset, and then we can get the remaining ground points. These are the points on the ground surface. These are ground points. We can interpolate them to generate the digital terrain model. And this might be the final product. In this case, this is the digital terrain model after the interpolation. This red line here. Okay, by applying this kind of filters, we can, in the end, get this result here, which represents the digital terrain model. So this is LiDAR data before filtering here, and this is LiDAR data after filtering. After I generate the digital terrain model for this filtered data, I can represent this, for example, in this 3D shape using any kind of software. And this is our area after removing all of the trees in this case because it was a forested area. Now another important application of the LiDAR systems is in forestry. Let's take this example, the same area here, the same forested area that I have just explained on how to filter. I will take this sample here, for example, I will take just this sample here, and I will represent these LiDAR points in 3D space, for example, as you can see here. And this is what we call, in fact, point cloud. Because the LiDAR can penetrate the canopy of the forest, so we can collect information about the top of the trees, the canopy from the top, and also the ground surface. And this is very important. Unlike radar systems and satellite images, where we cannot get information about the trees elevations and also the ground elevation. If you look here, it's clear that this is here the ground surface, and here we have the top of the trees. And I can represent this in a different way. So this is the DTM, the ground surface, and here we have the canopy surface here. And this information is very important in the forestry industry. In fact, based on this, we can estimate the height of the trees, we can estimate the density of the trees, the wood content in the forest, etc. So this is one important application of the LiDAR systems. Another very important application, which is flood modeling, because we can generate very accurate digital surface models and digital terrain models. We can do different kinds of scenarios for flooded areas so that we can ring alarm in the event of that we have information, for example, that the water level would be raised by 1 or 2 meters. Another application of LiDAR systems is in archaeology. For example, let's take this very simple case. When you look at this aerial image here, for me, in fact, I can't see anything rather than just a forested area, and here I have here a forest, and then I have some path here, houses here, and then empty area here, etc. But using LiDAR data, after filtering, again, this is another important application of filtering LiDAR data. After filtering all of these trees here in this area, we can see something like this. This is now filtered LiDAR data. For archaeologists, These lines mean a lot, and a lot of discoveries, in fact, were based on this kind of filtered LiDAR data, because these lines might represent foundations for old walls or buildings, etc. Whereas in this aerial image, we can't see anything. One of the most important applications of LiDAR system is mapping the power lines. This is an area which wasn't possible, in fact, without LiDAR systems, where laser pulses get reflected highly from the wires of transmission lines. This information is extremely useful for knowing the tower locations, the structural quality of the towers, determining the model of the lines, and carrying out vegetative critical distance analysis, and also for carrying out repair planning, etc. Okay guys, that was a quick idea about the basics of laser scanning systems or LiDAR systems and some of the main applications. Of course, as you know, there are a lot of other applications that you can use and apply. I hope that was useful. Thank you very much for listening and enjoy your time. See you soon. Bye now.